Starting recording. Okay, so grad students are not here, but Marisa just told me that I did not post the recording from previous class. Do you guys? I think so. It's good, but you are in undergrad, right?
It's a separate e-class.
Yeah,
So
yeah.
I'm just curious.
Check it, please. Because maybe it doesn't look like it because I know that they made that ridiculous that I have separate classes for classes that are literally the same, but I know that and then I always have if I have can I put something into one I put I'm not saying it's possible I mess it up, but it's not it wouldn't be unusual. Okay. Hmm. Short lecture, short and hard. We are diving into the real physiology. So if you think this is hard, wait to get unit 7 to nitrogen cycle and then biogeochemical cycle. But this doesn't go to midterm. So midterm is next class on 15th, if I am not mistaken. It will be here. Um, so and then we will end up with unit 5 for the midterm. So when we start talking about bioenergetic and what bioenergetic means for us, it's important for me to tell you a little that you like the way how you need to see microbes to understand microbial physiology and energetic is as a chemist of the world. So that basically means that you have to understand basic chemistry, uh, chemistry of life to be able to understand the metabolism of operation. So uh, we call the organisms that use the light, which are plants, algae, and cyanobacteria, the physicists of the world. Uh, we are humans, we are biologists of the world, but microbes that are able to extract energy from majority inorganic and organic compounds, literally from any single molecule. Uh, not any, but majority, like microbes are able to extract energy from both the organic and inorganic compounds, but um, so again, I'm never going to ask details about chemistry and physics here because you have enough to memorize, but I am giving a little bit of introduction of thermodynamics of the microbial living system. So when you talk about energy, like energy cannot be created or destroyed, just redistributed, like changing the shape. But total energy of system remains the constant. So that's basic dynamics. So what that means from microbial perspective is that microbes are actually performing a variety of reactions to redistribute energies and to make it more for themselves. And they're doing that through types of reactions that are called oxidations and reduction. Uh, and the point is that they literally can extract electrons and energy from any compound that you give them. So, no matter what they are doing, well, from what they are extracting energy, the energy of the old system is in equilibrium, and it's totally different than the one from the surrounding system, which means that microbial life is actually in dynamic disequilibrium in terms of thermodynamics. So what means dynamic disequilibrium? Again, this is only for your information. I'm never going to ask you to write about that. So dynamic disequilibrium actually is built on two opposing forces. Uh, internal equilibration process or homeostasis, uh, and external forcing variables, which means, so what means homeostasis? Central carbon metabolism in biochemical reactions that includes carbon and nitrogen salts that get distributed. So that's that internal equilibrium. And then you have external forcing environment, which actually act against this dynamic internal equilibrium and maintains this dynamic equilibrium, which means sort of that all factors that can make this balance, like anthropogenic factor, natural events, global climate change. But the whole point is that what organism is doing internally is getting anything that has high energy as a substrate and use it to extract electrons and produce energy, and then that energy gets redistributed into the organism to make biosynthetic power. The least energy can be measured, and it's the amount of heat that can increase the temperature of 1 kilogram of water per 1 Celsius. Again, don't memorize this. This is pure thermodynamic. But the point is, the different microbial compounds that are used, the different compounds, whether they're organic or inorganic, have different amounts of energy that they can be paired with different molecules that will accept those energy, pay the electrons, and create more energy to get it to the biosynthetic purpose. So it's all about physiology. Now, that's the first law of thermodynamics. Second law, thermodynamic, is building on the disorder. Entropy, which means entropy is constantly increasing, like chaos. From that perspective, reactions can be endergonic, and exergonic. Endergonic reaction is the reaction that requires energy input. Exergonic reaction is the reaction that produces energy. We will always recognize endergonic reaction. I will show you that later on. We will always recognize endergonic reaction because you will see consumption of ATP to ADP and NADH oxidized to NAD+. That would be endergonic, which means it's spending an energy. If you see opposite, ATP to ATP or NAD plus to NADH, that would be exergonic, which means that reaction will release energy. So that's how you will always know which of reactions is energetically stable. Again, exergonic, production of ATP or NADPH, endergonic, utilization of energy. This can come to the final exam. I do like to ask questions about endergonic and exergonic reactions because to me that's really logical. You don't really have to memorize a lot. You just need to understand. Oops. When you transform substrates into the product, energy created or released is used for biosynthetic purposes, and the bacteria microbes are making bioenergy. So during substrate to product transformation, the free energy released is called Gibbs, not Gibson. So again, in terms of how is Gibson energy or free energy of the system during substrate conversion relating to product. So in exergonic reactions, where you have that ATP production and NADH production, like high energy, delta G or the free energy has a negative value. So you see minus, that means reaction is energetically favored. And of course, in the opposite, endergonic reaction, if you need to invest energy to create substrate to product, the free energy has a positive sign, which means delta G will be positive, which means this is non-favorable reaction energetically. And you will hear very often in next slides oxidation and reduction. So you probably heard it till now multiple times. So during oxidations of substrate, microbes are performing a set of reactions in literally a stepwise manner, like step by step. And the point of these reactions is to release more and more. You've probably heard about cells that extracting electrons to fill them. No, the energy that is released depends on the substrate and on the product that will be made in the reaction. So that will determine the sign in front of the delta G. Again, don't memorize these reactions. All what you need, I'm just giving here an example how to recognize when reaction is exergonic versus endergonic. Oxidation of methane, that's what I really like. So the oxidation of methane to methanol actually has, so it gives you the calorie, the energy, the number of how much energy is between methane versus methanol. And if you look those four electron donors, methanol, formaldehyde, and formate, you can see that they actually have different kilojoules, which means they have different energy values, which means time. That minus time can be instead, right? We have the energy. So all these reaction is exergonic because it has minus sign. So, but again, the amount of energy released will really depend on the substance. Uh, Again, just know how to recognize what means negative sign. So, brief example: the methane has energy of 800 something kilojoules. So when you oxidize methane by famous enzyme MMO, you get methanol. Uh, and methanol has a energy 727 kilojoules. That means that you release 153 kilojoules, and negative sign tells you that this is exergonic reaction. Then you look methanol versus formaldehyde. Again, methanol has 727 kilojoules, but the product of methanol oxidation is 568, which means there is a difference between 159 kilojoules, which means it's exergonic. So again, every substance is different. So the energy released, that 150, 159, is captured along the way, and it's used to deliver protons across the membrane, and those protons across the membrane are creating proton motive force that will be later used in energetic process. One of them we mentioned in the beginning, flagellum synthesis. Now, all those stepwise reactions that are physiological, again, we mentioned many of them multiple times. They're all happening during electron transport chain, and when that electron is getting extracted from various donors and moving toward various acceptors, that will be that jumping from one to another carrier that will be followed by proton motive force generations. And we already talked about electron transport chain when we talked about the Redox way of proton motive force generation, where we see set of oxidations and reductions on quinones on cytochromes in the membrane, which is followed by proton transportation, which is used to energize them. So again, I always ask this, even though I assume you know, did you ever hear about oxidations and reductions, and do you know how to recognize it? Okay, so my first year teaching this class, people didn't know, so that's why when I introduced this, so I will just briefly remind you what means oxidant, what is red. So, and the reason why I'm saying this is because I always ask, define reductant and oxidant. So I can give you compounds and ask you to write me whether it's oxidant or red. So what is reductant? So reductant will be the molecule that has a tendency to release electrons and become oxidant. So those would be highly reduced compounds, compounds that can be electron donors. Oxidant, on the other hand, is a compound that has a tendency to accept electrons and become reduced. That means it would be terminal electron acceptor, or TEA. Again, this is really, really important. That's something that I always ask in biology. Just like structure is slightly different. So you don't immediately understand my acting. So the best electron acceptor in biology is oxygen. Oxygen can accept 2 electrons because its redox state is 2. So reduced molecule, on the other hand, has a tendency potential to lose electrons. So oxygen, as a terminal electron acceptor, the best in the world, has a tendency to accept 2 electrons. So its state is -2, while pure sorted molecules are reduced. Now, the same how ultimate ultimate terminal electron acceptor would be oxygen, the best or ultimate electron donor will be hydrogen. So the hydrogen each hydrogen atom can donate 1 electron at a time, which means redox state of hydrogen is +1. So oxygen can accept 2, which is -2. Hydrogen can donate 2, which is +1. So what you're doing, you are coupling redox potential to understand energetics of the cell. So what is redox potential? You will hear this very often, like redox negative, redox positive zone, like redox negative zone in the bottom of the ocean. What that means? That means there are many electron donors over there. So redox potential represents equimolar concentration of reduced and oxidized forms of molecule at like the equilibrium, because molecule can have oxidized or reduced version depending on what else is present. And as example, you will observe here oxygen and hydrogen as ultimate donor and ultimate acceptor. Sorry. So best reductant is hydrogen, and the oxygen will be oxygen. Two of them are perfect couple. So when you oxidize hydrogen, H2, that releases two protons and two electrons, right? The enzyme that is doing this oxidation is called hydrogenase. And so the redox potential of hydrogens has a negative sign, minus 0.4 something volt. Again, numbers don't matter. So what matters is that hydrogen has negative redox potential. That's how you will know. Oxygen is the one that is accepting electrons. Oxygen has plus redox potential, highly positive. So oxygen has like plus 0.8. Hydrogen is minus 0.4. So oxygen can accept two electrons and form its oxidation state goes to 0.0. So when you couple hydrogen and oxygen, you get some energy, net energy, donor and acceptor, which is like plus will be like 1.23 volt. And that energy difference between two half reactions will give you delta E or redox potential of hydrogen and oxygen together. How would you calculate delta G? Again, I never asked you to calculate. So literally this will never be for your exam, but it's important for you to understand how it's calculated. Just a brief reminder. So what is Gibbs energy? It's a free energy available in kilojoules. In biology, we express it per mole, which means the amount of energy needed for a reaction. Question is, do you have enough energy that can favor production of protonopsiphos? With a zero in the superscript is actually pre-Gibbs energy, and it's energy that exists in standard temperature. Again, never ever know this, but don't even try to memorize this formula. This is just reminder from a physics to understand what are we doing. So how you determine whether some reaction is energetically favorable or not? Well, you have to understand how many electrons have been transferred in reaction, and the difference is in the redox potential because the Faraday constant is constant. So that's what this is the formula. This Faraday constant is constant, number of electrons transferred, and then the difference in the redox potential between the reaction. So that's how you will know whether some reaction is possible in nature or not, and how many electrons participate there. So if you think about that last step, form to carbon dioxide, last step in method of today. So it's exergonic, potential is minus 0.4, because this reaction is coupled to the reduction of oxygen as a terminal electron acceptor. Again, redox potential of this reaction is 0.816 or 0.2. What's the difference? The difference is 1.2 or minus 1.2. So this will be your redox potential, like the difference between two half reactions. So oxidation of formate to carbon dioxide coupled to reduction of oxygen. So formate will be electron donor, oxygen electron acceptor. Formate has minus 0.4, oxygen has plus 0.8, so the difference is 1.5. The question that we ask is, so we know Faraday constant, we know delta E, redox potential difference. So how do you determine how many electrons are participating in this reaction? So you know that each oxygen atom can accept 2 electrons. That's his state, minus 2. So when you put that into equation, so you're going to have to know, you will see that the energy of formal oxidation gets to be minus 234. So this is literally the formula that we would use. Again, don't memorize it. So I just replaced it with Faraday constant 96.48. So when you couple formate as electron donor and oxygen as electron acceptor, there is a difference of 244 kilojoules. That means reaction is exergonic. And we can calculate how many electrons are participating in this one. And we see that 2 electrons oxygen can accept because his redox state is 2. Why would the number of electrons be important? Because we need to know to understand how we need to know how many electrons go participate in the reaction to understand how electron transfer chain functions. So you can understand how much energy can be generated. Now, if you think about ammonia oxidation to nitrous acid, again, HNO2 is the formula. So how many electrons would be transferred in this reaction? So what you need to do, you need to look what is your reactant, what is your product. So half reaction, so you split it to half reaction. Half reaction, one ammonia to nitric acid, HNO2, half reaction 2, oxygen reduced 2. So how many electrons would be transferred here? So if you look redox potential of the nitrogen. So you look the nitrogen atom. So what was the redox state in the first reaction, and how redox state changed in the second reaction? So how did it change? So if electrons have been lost, again, the redox state must change because when they accept electrons, they become more negative. So you need to know what's the redox state in ammonia and see what's the redox state in nitrous acid. Again, this might be this chemistry, but it will help you to understand. So when you compare redox states, you know that reaction happens. So each hydrogen has redox potential 1, plus 1. We see 3 hydrogens, that means plus 3, right? Ammonia is uncharged more. So that means that nitrogen must be minus 3, right? So if the plus 3 hydrogen is minus 3 nitrogen. The product is nitrous acid, HNO2. So what's the redox state of the nitrogen? So again, you know that hydrogen is plus 1, right? But how? So this is you know this is plus 1. You know oxygen is minus 2, and basically to get it neutral, you can see that nitrogen in nitrous oxide now has a redox state minus 3. So it went from plus 3 to minus 3, which means what? 6 electrons got transferred in this reaction. Does that make sense? Let's see if you got this one. So literally this was plus 3 to minus 3. Okay. So how many electrons have been transferred here? 2, 4, 6, or 8. How many? So which one? What will you look? What do you think? Sulfur. How? Hydrogen plus 2. Hydrogen is always plus 1. We have 2 plus 2. That means your sulfur is minus 2. What is the oxidation state of sulfur and sulfur intensity? So oxygen is minus 2, right? Minus 2 times 4 is minus 8. Hydrogen is 2, is 1, and it's just that's what? What's the difference? It needs to be uncharged. It's plus 6. So it went from minus 2 to plus 6. How many electrons? So you leave 2 up to 0, and then plus 6, that's 8 electrons. So 8 electrons were transferred in this reaction. So why are we actually doing this deterministic number? We are doing it to recognize the free energy and estimate if reaction is favorable to create proper force. So that's why we need to be able to determine how many electrons are transferred. That's why we need to know the oxidation state in both substrate and product. And again, can be, it's really chemistry, so I'm not going to ask you to calculate. If reaction is releasing energy, that will be exergonic. If it requires energy input, it's considered endergonic. If it's exergonic, delta G will be minus. Mm, If it's endergonic, delta G will be plus. So exergonic reaction usually starts with the molecules that are highly negative, and they have to have more negative redox potential, and it will end up with a molecule that has less negative or more positive redox potential. So that will be, again, previous example, hydrogen and oxygen as a perfect couple. Hydrogen is reductant, oxygen is oxidant. It's highly energetically favorable reaction because it releases enough energy that we can use to create proton-motive force. Exergonic reactions, which we know have negative delta G, are considered to be catabolic, while endergonic reactions are considered to be anabolic. Those are some terms that I will always have. So, in endergonic reactions, electrons move from molecule that has more positive redox potential to the molecule that has more negative redox potential. In exergonic reaction is the opposite. Electron moves from those that have more negative to more positive redox potential. So when something is highly redox negative, that means it's very abundant with electron donors. Again, as I mentioned previously, if reaction is exergonic, you will recognize them always when you see production of ATP or NADPH. If it's endergonic, you will see consumption of ATP and oxidation of NADPH to NADP plus or NAD plus. Again, I'm pointing out this constantly because I ask these questions. NADPH or NADH is oxidized to NADP plus or NAD plus. NAD plus or NADP plus is reduced to NADH and NADPH. Each of these oxidoreductions have to be usually are coupled, and in next metabolic reactions that we will cover when we talk about central carbon metabolism, you will be asked which molecule is oxidized or reduced. So you will always know based on reduction equivalent. If you see molecule X, molecule Y, in between them you see like an arrow and said NADH, arrow oxidized to NAD plus. That means it's coupled to the reduction. That means that molecule X got reduced to molecule Y. Reduction equivalent NADH was oxidized to NAD plus. So again, it's all logical, so there is no much memorization, and it gets even more clear once when you see this tower of power, which is the queen of microbial physiology. It literally, this is all what you need. Functions. Okay, if I ask question about this, I always use the state. So, power on the top of power of the tower will be molecules that have highly negative redox potential that are classified as a good electron donor. On the bottom of the power of tower, and you can see that minus redox potential. On the bottom of tower of the power, you see molecules like oxygen that have highly negative redox potential with a good terminal electron acceptance. All what you need to get energy production, this is what microbes did in past, in earlier, is to find the best couple. Find the best couple in between acceptor and donor. So who is the best? Hydrogen and oxygen, because there's such a big difference between them. So if you think about how electron moves from carrier to carrier, and if you think about how long distance that is, think about how many electrons get transferred, which is followed by proton movement across the membrane, which is followed by gradient, which means energy. So it's easy as it is. There is nothing unclear in this one. But if it's a short distance there, it's a little bit messy. So again, the most efficient is oxygen as a thermal electron acceptor. The most efficient fuel is hydrogen, but also organic carbons, like glucose, they're all on the top. So hydrogen and glucose are noticed to be the most energetic, like the highest, the most energetically negative, like high redox negative, most redox negative potential on the planet, while oxygen is redox positive. So again, we'll talk about this a lot when we talk about central carbon metabolism next class. And the example is the sugar that gets metabolized through glycolysis. So when sugar gets oxidized through glycolysis, like you know how you have glucose, then you have glucose 6-phosphate, fructose 6-phosphate, fructose 1,6-phosphate. That is all metabolic pathway of glycolysis that you probably all know about. What you get through that glycolysis, there are certain reactions when you will get NADH produced and you will get ATP produced, and both of those react like it's a very low energy yield though, but NADHs that are formed through glycolysis can also be shunned to the TCA cycle. And if you think about aerobic metabolism, pyruvate gets converted to acetylpyruvate goes to TCA cycle, and in TCA cycle, you will have those reduction equivalents, NADHs and FADHs made. Where will they go? They go to electron transport chain, to complex one. If you remember electron transport chain, when we talk about redox loop metabolism, NADH is the first molecule oxidized by NADH dehydrogenase, and electron is extracted. So that all happens on complexes 1, 2, 3, 4, while complexes 1, 3, and 4 are proton pumps. Again, that energy of H plus gradient will be used by ATP synthase to make ATP. So in order to understand microbial respiration, and the electron chain, because I mentioned, is the most simple one and the most common, not most simple, but most common one in aerobic organisms. But there are many other types of electron transport chain that we will cover, and all what you need to understand the electron transport chain in microbes is understanding power and then negative potential. So that's all what you need to know to determine whether bacteria can generate energy. So the way how tower of power is arranged from top to the bottom, the most negative redox potential molecules are on the top, and then below is little left, and on far bottom are molecules that are with the positive potential. So top are fuel sources, but they are arranged by strength. So the one that is on the top is the higher, then the one below is less energy, and so on and so on. So reductants, top of tower power, oxidants, but technically you can couple molecules. Not all of them are so good, which you will see later. So which one is good couple? The one that can produce the most energy. So hydrogen technically can be a good electron donor for everything, because you can pair it with literally any oxidant, it will still generate energy. So the distance between electron donor and acceptor will determine how good a reaction is. Greater distance, greater energy distance is the greater energy potential. So the difference in between energy or that pathway determines how efficient cell will be to make proton multiple. That means, for example, if you pair hydrogen with here, right, will be minus 18. But if you go down, nitrogen is better electron acceptance with hydrogen, oxygen is in back, so more energy you get. So, for example, some stupid oxidizers use hydrogen sulfide as the electron donor. What can they breathe? What can be the electron acceptor? Only something that you feel, so maybe iron is one. But what cannot be the receptor, for example, it cannot be lucky, because it's very short distance. So you find the perfect match. And that's what bacteria did. That's what microbes did during the evolution. Again, the most efficient reaction, hydrogen, oxygen, because hydrogen is highly redox negative. But bacteria have a very good growth if they pair highly reduced fuel source with a very good oxidant. It can be oxygen or nitrate, nitrate, but nitrite as well. So this is what microorganisms are actually doing to generate energy. So they could do pairing between reductant and oxidant. They have very close redox potential. But in this case, that would be fermentation. So organisms that couple those like molecules with similar energetic potential, they are not doing electron transport chain, they're doing fermentation, and the way how they generate ATP is not on electron transport chain, it is done through substrate level phosphorylation, which we will talk about next class. So those fermentation organisms are famous by that. So usually organisms that are using those endergonic reactions to create energy, they are living in syntropy, which means they are living closely associated with some organism that can help them providing reduction equivalent. Just a few questions, like just so you can understand. Which reaction would have the lowest potential for energy yield? So, and then you literally see these redox potentials here, like minus carbon dioxide to glucose, nitrate to nitrate, nitrate to nitrite, sorry, iron 3 plus, iron 2 plus. So which one has the lowest potential for the energy yield? What do you think? When would you get the lowest energy? So look these three, yeah. So neutrality to the potential, so this reaction. Which of them will give you the lowest energy? Okay, let's see. So we go from A, glucose, 1.25 volt, 0.25. Sorry, was right? Yes. So, and this is exactly, you don't even have to look at the potential. You can literally think the way how Elizabeth just explained. Where is iron on the tower? Where is oxygen? Where is it? So glucose is here. Okay? Oxygen is here. So what is this? So this is glucose. This is nitrate. Nitrite, sorry, nitrate, nitrate. Okay? So we go forward. Still three good. Now iron would be here. Oxygen is here. Is the distance shorter? So lower energy. Easy. Now, oxygen, really not the only electron acceptor that we can have. We just saw that nitrate and also nitrite can be electron acceptors. Oxygen is the best, but remember, oxygen was not available always to indicate. So all what microbes need to do when they find themselves over there in nature is to evolve different mechanisms to couple respiration to couple respiration from more negative fuel source to more positive electron acceptor. Again, we breathe oxygen, but microbes, so we are aerobic, microbes do not get to be anaerobic. They can be anaerobic, they can respire other molecules, and we will cover all of them. If somebody took my class last year, we have all actually we talked about available alternative electron acceptors. Why microbes had to do that? Because in early time in evolution, there was no oxygen present. until cyanobacteria created big oxygenation events. So microbes learn how to respire and metals and sulfates and ions. So they can literally, the whole point is to find the perfect couple, highly negative electron donor with highly positive electron acceptor, because that movement of electron will create proton multiforce. And again, these are just some of the options, terminal electron acceptors that you can have. The point is more negative fuel source to so basically what you need to have, so when you have more negative fuel source, you have to find positive that you can calculate. And don't get confused. Respiration does not always have to be considered aerobic. So it can be, I know that usually we think about anaerobic, we think about respiration as like purely oxygen involved. No, it can be branched, it can be different, it can be anaerobic. If the terminal electron acceptor is not oxygen, that's called anaerobic respiration. And this similar concept, like we talked about this microtransport chain in mitochondria. So obviously I'm not going to read over that because this is just repetition when you read when you talk about proton storage generation. So you have all those complexes, complex 1, complex 2, 3, and 4. Right? Quinone pool associated with complex 1. But the point is that proton multiforce is generated. And similar concept exists in bacteria because mitochondria are bacteria. So microbes literally evolve different electron acceptors, electron transporters to generate energy. So NADH is not the only molecule that can start the electron transport chain. It can be various different molecules. Again, this is all from your majority of this we covered when we talked about what did we talk about? Proton multiforce generation, those 4 ways. So but since this is really important concept for electron transport chain, and now it is 12:10. I'm thinking to stop here and then to move on to how many slides I have. Okay, let's see how many slides I have. I just want to yes, I have a lot. So I don't like rushing through things because this is really something that I will ask in details in exam. So how about we stop on electron transport chain? You will digest it a little bit. Oops. And then next class we will finish about electron transport chain in anaerobic and aerobic respiration and move immediately to central carbon metabolism.
Time what? It should be 1.5 to 2-ish